Hey, hello. Okay, my hat is where. Okay. Oh, so I'm back. I know. Times fly, right? So we got not interrupted, but in the middle, trying to explain all these AI stuff using MATLAB on part one. But now we have many time to cover all, right? So hi, first of all, for the ones who are joining us. Hey, my name is Alberto, and I'm from Mexico. I'm your happy um, Mexican MLH coach. And in this session, we were talking about how to take advantage of MATLAB's functionality of the network neural network designer. In part one of this series, we were discussing classification network for handwriting numbers. We were taking a look to the data set, which was a very, very good data set that MATLAB provides to us. This is from their tests or examples or their guides to the toolbox, because remember in MATLAB the packages or well libraries etc are called toolboxes. um, and we were declaring or creating this neural network that takes an image input and predicts the number. The requirements are that the image must be 28 by 28 pixels in black and white with the black font and white number. And well, that's it. So let's return to the code. If there's any question, you can always watch the recording of the past session. And also, there is another session I give on last Friday, which is a theoretical introduction to machine learning that you can watch if you have any question, regardless the concepts or what is happening here around the artificial intelligence world. In that session, I covered like the whole picture of what artificial intelligence is current right now in a theoretical aspect, not for the mathematical background, no, for the key concepts, I would say. So I see some comments here from Abhinav Malik. So hey, hi, from Sparky Circuit student. Hello everyone. Hello. Nice. So, I also like to give some time for people to join. I give 5 minutes for the past session to this, but I think doing a little recap it's not going to hurt anyone, and helps for the concepts to be very present, right? So let's do that recap very quickly. Let me share my screen. So here we are. Again, this is the Create Simple Deep Learning Neural Network for Classification in the MATLAB docs. I will share the link to this file later. No, right now. Right now. Well, actually, in your MATLAB, you only need to copy and paste this comment. Give me a second. Mm, mm, yeah, create image classification, training, basic. Yep, is this one. So here's the comment. And what we were mentioning, it's the the flow. No, I don't have this open right now. Give me a second. We were mentioning the workflow of many many MATLAB flows for artificial intelligence. Like the first part and the most important one, I will say, it's the data. Once you have your data, you probably need to organize it and process it, and based on data, find the features or the important things among this. Based on that, you build your model, you evaluate your model, and you iterate. Right. So that's from previous session. Right now, we were discussing that the data set that we have, it's very, very good because it's already organized on the folders and it is even. What that means, sorry, it is balanced. What that means is that we have the same count for each label. In this case, remember, we were talking about handwriting digits. So we have a 0, 1, 2, 3, 4, 5 until 9, right? We were discussing that if we don't have an even data set, meaning that, sorry, not even the balanced data set, meaning that, for example, we could have 300 of these zero images, 1,000 of one number images, just 500 of two number images, etc. We could make some synthetic images trying to balancing it, for example, rotating the images, making zoom in, zoom out, etc. But again, the best thing to have is organic data that was generated by the main source from all of the images come from. The other thing is that, for example, we could work with that, but there is a problem. For example, if we had a two number, a number of 100, just two numbered images, the model probably will have problems trying to identify the number two because it was trained with less data that with the other numbers. Um, but again, it's the ups and downs. For this case, this data set, it's balanced, it's already classified, it has a dimension set already that it's 28 by 28 pixels, plus it's black and white, which means already the background it's white and the number of, well, number it's defined in ones. That's a matrix, a 28 by 28 matrix, one of one dimension. Remember that if we want to work with color images, we need to define a color schema that can be RGB. Um, and then the matrix will be three dimension 28 by 28 matrix. That will be more computational power required for that. So we define the training files for this. Remember, good practice is to define your validation here. The example sets just a training and a validation partitions. I recommend also to give a test or to set a test partition. In this case, we will try to use an image from our own to test this. And then, well, we define the neural network. Remember, this neural network it's formed by the input layer. This layer just receives the image. Uh, the image here it's set to be a 28 by 28 by 1 dimension matrix. The convolution, sorry, to the layer, the batch normalization layer, and a Rayleigh layer. This block right here it's separated due to a reason, because The image input, it has one intention. Then these other three layers has, let's call this a block, has another intention. The max pooling has another intention, and these two are repeated, one, two, in the case of the combination to the layer another time, and then a fully connect layer. The intention of the fully connect layer and the softmax is just to say which one will be tagged with the parameters we want. In this case, there are 10 parameters, sorry, 10 labels, or 10 ideas from 0 to 9. Um, Being funny because MATLAB, it's not a zero basis index, which means it starts counting not from zero like many programming languages, but from one. So let's see how to resolve that. Do you want to? Um, but now that we had time, let's take a deeper look on what's happening here. We already explained that the image input layer takes the image with the size set, in this case 28 by 28 by 1 pixels. The computational layer, we were explaining this as being a filter that reduces, in most cases, the matrix when it's passing by. But we were talking that when you reduce it with a computational layer, you have to do a mirror of the compilation to get the expected size of the output. Meaning, for example, that if we want to segmentate an image, for example, we want to get the n by n size of the image, and the output should be the same. In this case, what we're doing is that we are adding a padding here. The padding, it's an extra, like a border, but it's not the border, it's the padding of zeros, um, that ensures that the output of this filter, in this image you will see kernel, you can take it as equals. Kernel and filter are the same. It depends on the literature you're reading, but it's the filter that takes this as an output. What happened? Well, it's matrix multiplication, just like that, and the output it's stored in another matrix. Well, what's the purpose of that? For the neural network to try to start understanding what's happening in the image. The neural network start getting what's happening inside. Again, it can be a very, very black box for us. There's a dedicated field in artificial intelligence right now, which is trying to make neural networks more clear, like a field that's trying to apply, how to say, algorithms, techniques, even already made pieces of software that give us information that's what's happening inside there. Well, this combinational layer, it's connected via a batch normalization layer to the ReLU layer, which is the activation function. This normalization layer um, normalize the activation and gradients preparing through the neural network, making the neural network training easier, like an optimization problem, right? And this is necessary to connect to the ReLU, which is the activation layer. The most common function it's ReLU, but there are many activation functions here. Um, well, to you for checkout later, you can always click on these links, and you will be redirected to the MATLAB documents for this. Then the middle max pooling layer, that it's between the combination block, uh, from each combination blocks. Sorry, the intention for this max pooling are that reduce the size of the feature map and removes the redundant spatial information. It makes possible to increase the number of filters in deeper computational layers without increasing the required amount of computational per layer, which creating for max pooling. Okay, um, I think this deserves the time to check it out more. So here's the documents for that. And let's see if we can make it a graphic way. Max pooling layer. Hmm. Okay, this it's kind of it. Um, See the colors here? Well, we ask ourselves which one of these values inside the defined kernel or the defined filter has more valuable information for us. Well, probably the one with the highest value. So the input is a 4 times 4 matrix. The kernel it's or the filter it's defined as a 2 times 2, and then the output will be that. Getting the higher value, which give us the more representative information in that part, and that's for getting or making easier for the model to process this huge information. In this case, it's a 28 by 28 matrix, right? But that's low, very, very, very low resolution. Imagine of an image with high resolution. Even though, imagine an image with higher complexity than just black and white with many colors. So the RGB map will give us values not only from 0 and 1, but from 0 to 255 values, or 0 to 1, but in a more complex scale like 0.1, 0.2, 0.33357, etc. Right? So making this max pooling it's that it's maximize the the result here, get that into a smaller matrix, and then I can process that. In this case, it's a two-dimensional max pooling layer that downs the sampling and divided the input into rectangular pooling regions, then computing the maximum of each region, right? So I think that helps to understand better. You get this, you get this, you get this. There are different techniques when doing the max pooling. In this case, we're applying this because we are not expanding from more than the colors here, for example. But we can do a 3 times 3 that will have four, no, sorry, one, two, three, four, well, actually eight values of the matrix repeated again in the next ones, right? You can see here. The only one that does not repeat itself, it's the one in the corners. Or this other one, when we do this and we make the operation two steps instead of one, well, here we define the step. Um, it's called stride. If the stride it's two, in this case that the matrix it's 4 by 4, then no one we will be repeated. If the stride it's one, then again we will be repeated. Then here again, it's tried it's 2, but the pool filter dimension changes. So here we advance 2, and then we advance 2, and we have to create like right and bottom padding, right, to make this possible. Which is better? It depends on you, actually. It depends on your case. And I will say try them and see which one fits better for your model and gives you better results. How you can test that? At the end of all, there is an average. Well, there are many ways to check which one results you better. In this case, we check the accuracy of this. But let's return. That's the max pooling, right? So the the values that the max pooling here receives, it's the size of the kernel or the filter and the stride. In which one we decided it's 2 and 2, which will make us a filter like this. So this will be more um, alike for our model. So instead of 4 times 4, this will be a 28 by 28, and the output will be the size reduction of that, half of it, 14 pixels. What else? What else? What else? So we have the max pooling connect between the convolution layers, and finally the fully connect layer. So in this one, again, we take the output parameter to match it to the corresponding classes. Here are 10 corresponding classes, and the softmax, finally, it's the activation function to normalize the output of the fully connect layer. Given though that once we train this, actually let's going to run. Okay, I need to run this again, I think. Give me a second. Okay, it's running. So another thing I want to say is that please feel free to ask any questions you may have during this session. I mean the okay, one step before that. Oh yeah. Um, what was I saying? Ah yeah, the whole intention of this it's for you to uh, be with no doubts. Or no, maybe. I always say that if you have more questions at the end that at the beginning, it means you're learning. The thing is to not have the same questions every time, right? Okay, so what's the problem here? This was working just fine. Okay, nice. A comment here from Shumeri. Hi, it's your Sparky Super student. Oh, I noticed my My computer is kind of slow right now, so that maybe it's another thing here. Okay, good. Run this. Okay, nice. Okay, now this. But I have this installed. What's happening? Okay, let me close this and open it again. That may be the best thing I can do. So let's call these quick break for my computer to start working again. Can you hear the music? I mean, it's not mine, but I think it's a neighbor or someone here on the street playing some music. Um, which is funny. I just hope that the algorithm doesn't hear it and think it's copyright. That's my concern here. Not really. A little only. It's cool. Okay, amazing. Okay, it's happening again. Sorry for that. I I should restart the computer when I had the chance on the break here. But when the last session was done, I went to have breakfast and stuff, and now trying to resume this. This is kind of slow. That's why I wanted to restart it. Okay, let's take a look at this. For example, I found this better example of the function of the combinational layer connected to the max pooling. In this case, for example, if we had the, the filter applying or the kernel, you see how noise is reduced once it enters the max pooling. And again, this helps a lot. Um, this is another example of how this goes. The only thing here is to remember that the downsizing it's not for us because our images are already very small, so we want to keep all information as much as possible. Mm, okay, you see the error, right? So let's open this again. Come on, MATLAB. Hey Shimori, I was doing dishes while listening YouTube. I'm glad Alberto mentioned that you said hi so that I could came to my PC and reply. Hey, I needed to do dishes too. Yeah, it's amazing. I think we all do dishes this time. I'm not doing dishes currently, but I was just some minutes after starting this session. It's wild, like adult responsibilities, right? Which thing is the one you miss more? Like the pros and cons of living alone? Unable to communicate. Okay, I have some troubles with MATLAB. Let me restart again. What? Communication. It says restart your MATLAB, but okay, I already was trying to restart it. Okay. There's another thing I wanted to show you. So I am going to take this time that MATLAB is not working for explaining this. Okay. Neural network architectures are complex and are defined according to what we need to solve. In this case, let's take a look at this diagram. This one, for example, the deep cumulational inverse graphic networks, it's probably a very common one, or the UNet neural network. Mm, there are better graphic ways of watching this. Mm, this is, for example, okay. Um, let's take a look at this to see the U shape of this. But this 3D one, it's better for us to understand. So we have the cumulational layer in orange, then we have the dropout layer in red, concatenate connections, and max polling layer, upsampling layer, and submax output layer. So receives the images in the convolutional layer. For example, this is a 256 by 256 pixels of 32 dimensions. It's received, it passed from one combinational layer to another combinational layer, then to a max pooling, then to another two combinational layers, then to another max pooling. That there's where it's reduced, then to another combinational layer, then another combinational layer, then to another max pooling, then combinational layer, dropout layer. This dropout layer helps for prevent overfitting, then another combinational layer, another dropout layer, another sorry, for the dropout layer to an upsampling, meaning, for example, that imagine you have an image and you want to get from that image my face. So um, a, 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 a good example of this, it's trying to get the background removed from images. So we need to train a neural network to understand what backgrounds is, like in this very live example. I don't know if StreamYard uses a neural network for doing this, but it can be done. I mean, in this case, the picture needs to understand what I am, like my like, training to shape a person. Then removing the background and then placing it back again in the same shape and the same size than the input is. So the input should be my whole image without this great merely hacking background. And this complicated structure, this complicated architecture, because let's be honest, it's huge, it's immense, um, learns how to draw a line in my shape, like in the whole contour, replace the background, and place a beautiful background just like this. It has problems, like for example, here my finger, it's detected, not detected, detected, not detected, etc. Right? Or sometimes the when you have black things, for example, the hoodie, like is this part of me? I don't know. I will place the background here. The thing here is that the output should be the same size as the input. That's it's called U shape. So we apply unsampling layers, and you can call it inverse convolutional layer. In this case, they are the same. For example, they are same colors, but you can call it again a deconvolutional layer. It's a convolutional and deconvolutional, convolutional or inverse convolutional layer to make the same process, but the other way. So deconvolutional layer, neural networks, right? So remember what we were talking for convolutional layer, we can make matrices shorter because of the filter of the kernel, or we can recover information from them. In this case, make it bigger. Mhm. There was a good graphic example of this. Mm, well, I can find a good graphic example of this, but looks like MATLAB it's already opening. No, again, what? Okay, I'm afraid MATLAB it's not opening. I'm at computer right now, so I will need to restart it. And don't worry, I won't end the stream. But let's give this a quick break. Um, but first, I'm going to return explaining this, and I see some questions here on comments. So let me resolve them. So we reduce the size of the input. We do the max pooling to help. Getting the information from these matrices. We do a dropout to prevent overfitting. That means randomly it drops biases and weights and etc. So it doesn't overfit because this it's a complicated process and it requires a lot of time, a lot of data processing. So it can overfit to the training data, and we don't want that because we want this to work for things that the neural network doesn't know yet, like the test data. But again, then we deconvolute, do an inverse convolution layer, how you want to call them, and we need to reconstruct the image again and again until we have the output same sized. And again, you're watching me. Probably mirror it because this is my right hand and you're watching the left hand. But you get it. And we can say the camera to mirror this. So that could be accurate. The last is the softmax output, which is the fully connect layer to tell the label is. In this case, this unit architecture, it's more not for classification but for these kind of things. Um, and the last thing, the concatenate section, because you can see the outputs are connected not only to the next layer, but the copy and crop are passed from the first to the last, from the second to the n minus 1 to the third to the n minus 2, etc., etc., etc. So that's how this architecture is defined. And we can talk about more these neural network architectures in a minute. I'll be back. I need to restart the computer to see why MATLAB isn't working currently. But here, for example, um, I don't always do dishes during your streams, but after 3 days straight of global havoc, my life wants me to get something done around here. Interesting. Um, then you got to do dishes, especially if you want to eat dinners. Yeah, that's true. I'll be making it, so I'll get some. Enjoy the code, attend streams, eat, repeat, do the dishes. Streams, cook, eat, streams, cook, repeat. Alberto, what a reasonable size to create these on our laptops PCs because they can get so huge. My recommendation is to not make them on your own laptops. If you're doing this on MATLAB, for example, you can run them. You can run them online. I mean that's completely valid. And if you're doing on Python on other programming languages, well, there is a collab for this, and Google lends you some computers. Even if, for example, if you don't have a dedicated GPU, well, you probably will need one, so you can lend Google's one. So do collab. Do collabs are great for this. If you have a dedicated GPU and you have a powerful but really powerful computer, or a computer you can only um, use for these purposes, like for training models and stuff, that will be great. But yeah, if you have a normal computer, a human computer like mine, that sometimes fails, like in this case, well, it is not possible. Another thing, for example, it's that I use Mac, as you see, and well, some models cannot be trained with here, for example. Sadly, I don't think this works for AMD GPUs. Yeah, exactly. Some models, some architectures, and some code are specifically made for NVIDIA GPUs. So that's another turn down if you want to do it on your own. But the good thing here is that you can do it online. In my case, for example, being a Mac user, I definitely can't. I mean, there are no architecture yet prepared for processing these on a M2 or M1, or not even in a M3 chip, right? So that's the thing here. I don't know if I asked you that question the correct way. No, that's cool. Like that's the way. You can use all languages you want. Like there's no proper way to say. Um, and it does not depend on the size of the model. I will say it depends on the size of the data. For example, you can pass three images to this model, and that will be not that bad. But you can pass 1,000 images to this model, and that's where the problem starts. Oh, I did not think about that. Thank you, like Kaggle 2. I was trying to code on my laptop, but I gave up. No, 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 that's fine. Don't give up on that. Like you can take the model and put it online and process it on the cloud. So leave any question or anything on the comments. I'll be back. I just need to restart my computer to see if MATLAB can work right now. So I'll be back. Don't leave. That will be 5 minutes or 10 at most. Don't worry. Leave you with some music. Hey, so nice to be back, and it looks like MATLAB is working good right now. So let's resume. Thankfully, but the bad thing is that I lost all comments. I don't know why. I thought StreamYard keep track of this, but if you ask something before this moment that I didn't reply or didn't read, please post it again because I cannot check them. So, we were talking about these layers and how we can build our own. Sorry, something appeared on my screen. We can build our own neural network. Well, now it's done. Let's open this and add it to the stage. Here, amazing. So, this defined our layer. Now that our layers are defined, Spark is equal student will through. Thanks for the heads up. Hi, welcome, Pauline. Okay, cool. We're good. Well, about the training options, in this case, we train the network using stochastic gradient descent with momentum, provided with SGDM, stochastic graded momentum, with an initial learning rate of 0.1. We can change these parameters to see how this fits to our network, right? For max epochs, we shuffle the data every epoch. The validation, it's image validation. I mean, we pass the same data we stored or we declared before. It's up here. Remember this. The validation frequency will be every 30, and the plots will say the training progress. We the metrics we want to check it's the accuracy, and the purpose will be false. Now, if you check this, this is running because I wanted to verify that this was working before starting or resuming the stream. Sorry. So let's see what the output is. Remember, we talked about the cool graphic way of MATLAB? Well, this command open this window, which is giving me the accuracy over time every iteration. So you saw the accuracy at first was very low, but this graphic is increasing while the time is passing by, meaning that our model is learning at a good but very good rate. At this point, the accuracy was over 85, which means that with 50 training epochs, we will have the accuracy at a very good point. But you see, this as a control system goes up and down, go up and down, up and down, until it stabilizes at the end of everything. Here, for example, we have the loss. In opposite of the accuracy, we want the loss to be very short. In this case, we have 232 iterations when the training stopped, and we had 4 epochs, learning rate to be constant, sorry, and at 0.01, the validation frequency every 30 iterations, the objective metric it was lost, and well, some other information and data from this training. But now the model is trained, this is no longer running, and we have our network or neural network here stored in this variable. The train net It's this beautiful window that MATLAB provides. Let's return this to take a little longer. Display the training progress in a plot, blah blah blah, monitor. The trainhead uses the view if available. This is related to what Shimari was asking. Otherwise, it uses the CPU. In this case, I am running it locally, so the computer is running on my CPU. Um, Even 232 iterations took a little, right? Not that much, but a little. It was not immediately. Toolbox CPU device from execution to label. Monitor leap learning training trust entropy. Wow, that was a noisy motorcycle. I'm sorry about that. So then, finally, we store the scores with the min batch predict function that takes the net and takes the validation images, right? Because we stored this before. Then the Y validation, it's an scores to label, and we calculate over that the accuracy, calculating that using the mean of the Y validation and the T validation. The T validation, it's only just with the labels. That meaning which one was how to say this? Which ones was tagged with the right label? This comes from the first, very first declaration of the image data store. So that's how we can define these dot labels, right? And the accuracy of this was 0.99%. We have a very great accuracy of the predictions. So for this simple example, the creation of the layer was that not that hard, right? We just sorry, the creation of the neural network was not that hard. We define some layers, um, giving the correct functions in MATLAB with the parameters. This is all well documented. And then we give some training options and store it in a variable called options. And then finally, we use the train net to pass the data to train. In this case, we sort in this variable called images to be trained, the layers, the function cross entropy, and finally the extra options for this. The trainnet receives all these parameters and give us the neural network. This neural network can be applied later. And if you want to store this, well, remember that the net, it's in this case on the workspace, stored on a DL network. I think that's for deep learning. That's how they call this type of how to say this. Sorry, my mind goes blank. Um, Number, boolean, string. Well, this type in MATLAB, and we can store this. We can save this as save as, and this will be classification and write numbers dot mat, and we save it. So we're good, and we can close this trainnet. Now let's open this other one. Sorry. That will be do the same, but in this case, we are going to make use of the deep network designer. And again, I think this is really great for the graphic and intuitive way of creating this. Because an example like the previous one had an image input, three blocks of convolutional layers, and then the fully connect layer. But remember the unit architecture. Remember the other architectures we saw at the beginning. It can be hard or more complex to code, right? So let's start running this. The first step is the same. We need to unzip and load the data. We are familiar already with this data. It's the same data set. The digits in their folder with the name and etc. Then we create the IMs to be trained, the images to validate, and the images to test. In this case, we use a different validation schema, right? In this case, we are storing a test images, which is great. Then we open the deep network designer, and well, and it has the instructions for all of this, but let's do that. Let's open deep network designer. Okay, it's opening. Okay, here it is. It's loading. And the first thing we need to do, it's well, in if your case, you probably will be asked to create, yeah, this one, this one right here. Um, Take a look at this. The image networks already pre-trained. There's a SqueezeNet architecture, the Google Net, the ResNet 50, EfficientNet B0, DarkNet 53, DarkNet 19, ShuffleNet, and a very, very wide variety. Even more. I mean, there are plenty already built architectures here. And we can import them from PyTorch and from TensorFlow and even from our workspace. Because remember the one we said before, the let's try to open this. I clicked on import from the workspace, and we had this net in our workspace. Remember that? If not, here it is. This is the net. So this net it's a DL network with 14 layers. Let's return to the other file to count this. Train basic. Let's see how many layers. Exactly the 14. I was counting on my mind. Sorry, 1, 2, 3, 4, 5, etc. 14. It's okay. Meaning that this is the layer we created before. So, okay, that's fine. That's the one we want to import. Let's see how it looks in a graphic way. Right? So, wow, we have all the blocks, and even we have an input properties here. So the image input, it's named as that. The input size, it's defined and we cannot change it because we declare that. But we are going to create a new one, and this can be defined by us. It has the normalization dimension, the normalization parameters, a mean, etc. We can unlock it, but that will be create a new layer. The first computational layer that receives the parameters of the filter size. Check that if we do this, well, we can do it in a programmatical way, but here it gives us more information about the dimension, right? Because the other parameter was just 3, and we know that's a square matrix. But here we know it's a square matrix because it's a 3 comma 3. We can do a 3 comma 2 and a 1 comma 3 and etc etc. That's not pretty common, but again, it's not a rule. You make rules here. So if you want to try it with a 1,5 kernel filter, go ahead. Check the results. I mean, if that works for you, that will be fine. Then the batch normalization, the ReLU activation layer, and same with the max pooling. The max pooling had the put size at stride. Same here, because remember, not only we change from how to say, we not only do the step by step to the right, but from sorry, from row to row. So we move 2 rows, 2 columns. In this case, we can change it to be 2 columns, 1 row, and that will have the result with a different size. And we overlap again, and we process more information. And well, there's some many stuff we can do with this. Computational layer, batch normalization, and the ReLU. Again, computational batch normal size, and finally the fully connect layer with the softmax. The fully connect layer has the output size of 10 because we want to predict if it is 0, 1, 2, 3, 4, 5, 6, 9, etc. Well, just 9. So great to have this, but we are going to create a new. I just want you to check how we could store the previous one and use them later, because we have created a neural network, and it's under a DL network type of type in MATLAB. But we are going to create a new one, not with code, but with this cool. Are you sure you want to clear? Yeah, with this cool graphic way, which is the deep network designer. In this case, we need to start again with the image input, right? So we get this, we drag and drop the input, we change these parameters to fit our model. In this case, our images are 28 to 28 with a dimension of 1. That's nice. Then we add a cumulational 2D layer, remember. Then we add the batch normalized. Where is this? Here, batch normalization layer. Then we add the max pooling. No, the first ReLU. Where is the activation? Oh, here, activation. Check. I was mentioning that not only the ReLU, it's the only activation function. There's also the, for example, prelude, the leak ReLU, the clipped one, the tan H, and many other function layers. You can declare it on your own with MATLAB code, um, but most cases the ReLU works fine. I don't know why, to be honest. I actually I was having a conversation with a friend of mine that's called Chucho. If you're watching this, hello. Um, and we were attending a class of neural networks, and the professor told us that ReLU works perfect, and there are many papers that put ReLU as the activation function king, but for my friend, ReLU didn't work um, as the default function. He told me the default function he uses, but he told me with ReLU, my models simply don't doesn't make sense, that doesn't fit, or doesn't give me an accuracy that I want. The work of my friend Chucho is based off neural no sorry NLP, natural language processing. So again, it is not a law, but in most cases ReLU works fine. Then, well, this is just the block, but we created a previous network with these three blocks connected by the max pooling. Let's check out how many, or how's the accuracy, sorry, here for just one simple network. In this case, one, two, three, four, and five with the fully connect layer. And let's add the softmax. This is one, two, three, four, five, six layers of the network. So we connect them. Not that hard, right? Next, another thing we need to do is to verify this, so we can check here the analyze button. Let's take a look at that. Okay, and here the analyzer told us that this is fine. It has no warnings, no error, the six layers, and well, check it out, 251.2K total learnables. What's that? All the connections that exist here on the network, and this is a simple network with six layers, right? But check out all whole dimensions here, the learnable sizes, because this is matrices. This is working with many data, to be honest. Images, working with images is it's many data, and even these are one dimension, well, true, yeah, one dimension matrices. Even imagine working with color pictures extends a lot. Again, I know I'm very, how to say this, um, I repeat myself a lot with this, but just think about the whole consideration here. Well, we can close that once it's analyzed and we know everything's fine. Well, we can export it. And then for exporting this, it's going to be prepared. This is going to be called net underscore one. So we can go back here to MATLAB. And once the layer is created, remember, we still need to give some options, training options. We are going to use the same, the SGDM. Um, I cannot remember, sigmoid grade. I cannot remember the name. Max epochs. The validation will be the image validation partition we created before. The frequency, again, every 38 iterations, training progress. The accuracy is what we want to check as metrics, and the reports will be fine. And same, he used the train net to train this. So let me run this first. And you will see the output coming out. Come on, it's loading. So, this far, any questions regarding this? Okay, here's the train, the train net. So, 30 iterations. At this point, we are running our first validation. This will be the orange line um, to be drawn. Perfect. So, in first validation, we have a 50 accuracy, percentage of accuracy, which is like flipping a coin. But we hope that gets better, right? Let's wait until we hit 60 iterations. We are on our second epoch here. So let's go. Come on, come on. This is processing. Okay, nice. By this far, we are almost hitting 80% of accuracy, which eh, makes a great model with only 60 iterations. Let's wait until this finish. It's not even the half of it. Well, check the information of the training. We are on a learning rate with a low learning rate, but the result is good because on the accuracy graph we're seeing the increasing of the accuracy, which means model it's learning correctly. Yeah, we go up and down, but overall we are already around the 90% of accuracy. Um, I mean, remember this is all a network with just 6 layers, with just a combinational how to say this a combinational block, and I think it's great. I mean, the result is for it's great. I don't think this drop out like in the second. No, I mean like we're half of the training, and this is looking very good. So let's give a time for this to finish. And well, any thoughts this far? Like, are you enjoying this session? What do you think? Let me know. Okay, we're almost done with this. And I just see some comments here. All of your sessions are so good, but I got to say, this one is off the charts. Hey, thanks. I really like you appreciate this. Just enjoying. This is Sparky. Oh, Dave Conrad, you're Sparky. Oh, wow, cool. That's great because I thought I had to memorize two nicknames. Now I know it now. Dave Conrad is Sparky. Mm. And now the training. it's stopped. Great. The accuracy it's around 95, I think. I see it like 97%. Wow, that's so great. Let's return to MATLAB to validate this. Let's test this neural network. Remember, we have to have our scores. For that, we are going to use the net with the validations, with the min batch predict method, well, function here. Let's run this. Then the Y validation with the scores to label. And let's see how this accuracy goes. 0.9693. Nice. It's just very nice. And let's check on this for the classification. First, for example, we pass here um, 9, and this is a 9, 3, and this is a 3, 8, this is an 8, 4, and this is a 4. And even though it is hard for me to say this is a 4, to predict class it's a 5, and yeah, this is a 5, 0, and 4. Let's run this again because this is random, right? So we take the number validations with normal files. We make an index and on the writing validation numbers. So these all are random, and we plot this with their respective title, and we show the image of this. So let's run this again. Nice. And for example, here, this is an interesting one. I see here a 1, but we can argue that because if we make a very, very huge zoom, like with your eyes, just get closer to, to your screen, because I think I cannot do this on MATLAB, but I see a line here, I see some noise here that could make the computer think this is a 4 and not a 1. Could be. Even though this looks more to me a 1 than a 4, I mean, this is really hard, right? So the accuracy it's not 100%, and that's very hard to get on artificial intelligence like you probably want. And I'm not sure if that's a good thing to have like 100%. Maybe that means it's overfitting your model, and if you didn't do the correct, how to say, partitions of that, and you want to test it with test data after that, uh, and you get wrong results even though your accuracy is 100%, well, you know why. In this case, this for me, it's it's wrong. This is a 1 and it's predicted to be a 4. But in other hand, this one right here, it's hard to say for me. Like, I don't know what the person wanted to say with this number, the one with the handwriting, but the predicted class is a 4. So I can totally get that. Let's run it again. Oh, sorry, I hit the button here on stream. You're not with the MATLAB ID. Okay, again another weird four, another four, four, five, two, two, 7, 6, and 8. You know what? The the hard thing here will be to predict a value that it's not even with these input formats, right? So why not? Let's try to do that. I'm just need um, okay, number validation observation with the number files at x images predict class string y validation with the same index. We probably will need this, and I need to make another file with this. And let me see if I can get this on a JS Paint. The another the alternative account of a Sparky student tell us three blue, one brown covers the theory behind this subject on YouTube. It's a great video. Yeah, I do agree. They had very good videos, and well, go check out. Thanks for the link, Sparky. So here, let's say file image. Maybe Inkscape. Oh, I don't know install Inkscape yet. I thought I had. Mm, okay, configure page. No. File. No, I'm not hitting print. Why? Mm, I wanted to. I thought it would be easier, but I just want to create a 28 by 28 pixels matrix here. If not, I will have to create it with MATLAB. Why not? But that will be not handwriting. Ha ha ha. Maybe test image will be uh, 0 of 28. Nice. And zeros. One will be 1. Oh yeah, here. I just want to check something. Yeah. What I'm trying to do is nice. Uh, if you see these images as a pixel collection, you will verify that are like this. There are 28 pixels um, with a value of the of the black and white color. Um, so I will try to draw a number with this. I'm just going to make a straight line here, so it will be from the fifth value to the um, 10th value of the sixth column. This will be a one, maybe. Here, this one. Well, then I need to redefine the zeros. Um, exceeds what? Clear test image. What's happening? What? Index must not exceed the number of array elements. Where's the test image? It does not exist right now. Oh yeah, my problem. Delete. Funny thing about MATLAB. Don't know if you know this, but first I confused myself and I created a variable called zeros. And unlike other programming languages, MATLAB assumes that you know what you're doing and replace the reserve function zeros with your variable zeros. So I need to delete this variable because yeah, I don't want it. And now zeros refers to the built-in function. But yeah, now makes sense. And 10, it's so little. So 20. I'm just drawing a straight line in the middle of the canvas. And from the 6th to the 10th. And here I'm going to do the same. No, this was another example I was working on. Um, train the basic, create image classification, create image classification. So I have these and these. So I need to show this. Okay, nice. This will be the undefined. Nice. So what's happening here? It's I just um, let's make this create. Let me show title figure. I need to create a figure. No, delete this. I don't want this figure. Okay, open this on a tab. Okay, I open this because I draw uh, 1 1 1 1 1 1 1 line here, right? So this should be classified as a one for what we understand. Let's try to do that. Mean batch predict, we pass net slash one, which is the DL network we created with the deep learning, deep network processor. And here, image validation, it's not a data set. We create, we can do that. I mean, we could do that. Image validation. Mm, let's try first with the IMS test. What? What? It disappeared? Where my files go? Oh, here they are. Int test scores mean batch predict. Okay, let me check something very quick. This expects a data store or an image dataset or a numeric array. So, in theory, test image will work fine. So I make the prediction of this function and convert the scores table using this validation scores class names. Okay, I need to define the class names, but I think that's already saved on our workspace, so I don't have to worry about this. Yeah, no, don't need to worry about this. So then this could work. Let me remove this and this to see the outputs. And the category tell us this is a 7. So it failed. What happens if I test it with the net, which was um, the first argument we passed? Then the accuracy of this was better, if you remember, and the prediction of this category is accurate. This is a 1. Now let's try to create a 0, a square 0, and let's see if testnet 1 can make it. So I already find these. This is clean again. Now for these, I will do test image 5 to 20, but in this case, from what could be good, 18, 6, this could be 22, and it's 15, no, 4, so 18 equals to 1. Nice. I need the top, so test image from the 6th, no, sorry, from the 10 to the 18 in this case, and that will be from 5th to 20. I'm almost sure of this, so let's copy and paste this, and the only thing that will be different, um, 10 to 18, no, this is bad. It starts with 5, and then in 20 start, this is rows and columns. Well, I cannot remember. This is columns, then rows. Okay, yeah, yeah, exactly. So rows, it's 5 to the 20, 6 to 10. So I need to start on the 10th column and go down to the 14, since it's 4 long. No, it's 6 long, right? No, it's 4. And this goes from the fifth. Okay, let's run this. And now figure to see if the output is accurate. No, so I didn't move the values here. That this was the problem, but also I fucked these 14, 9, and 20, 16, and this is 5 to 20, 5 to 20. Yeah. No, I'm not sure of this, but let's try it again. I mean, no problem, no harm with that. Almost. For me, that's a 0. If I watch it, I will say it's a 0. Um, but we can change it. I mean, this could be better this way. Yeah, that's a perfect square. So this should be a 0. So let's predict it. Another time 7. This is weird. The net classification 1 was terrible, but remember, there we only use a zero, um, sorry, a one computational layer. In this net, without the underscore one, we use three blocks of that. We use the max pooling, and it's better fit. So let's take a look at this output, and it's predicted to be one. Um, Maybe if I run this all again, no, the output still one. So there's a problem with no handwriting because remember this was created with pixel perfect. So I should remove some borders and etc. for this to better fit. Uh, but yeah, I see a comment here. What are you working on right now? Well, we were testing the neural network designer, deep neural network designer on MATLAB. We saw how to create a neural network by code, fully on code here on MATLAB. Then we saw how to create it on the deep neural network designer. We watched the flow for a classification neural network and now we are just testing it with not the data set but with an image that we create on our own, and that's it. And we're seeing that this image that we create on our own, it's 28 by 28 pixels with just these values here, and it has problems for being classified. So what could be? Again, let's take a look on of the previous ones. These ones have not pixel perfect edges, but um, let's show this in show in. For example, the one should be this 8. So these, oh, that's another problem. These values are not from 0 to 1, but from 0 to 255. So my bad. We should check that before. So in this case, let's 255, 255, 255, 255. And let's run this whole again. Okay, now this is set to be a 9. Weird, but I mean, I that could be. Let's open this on a separate tab. Let's close this training progress. And I mean, for me, looks like a 0, but I get why this can be thought of a 9 and seems more accurate than a 7. So this makes more sense, like that. Um, the problem uh, of this, it's that again this is not a perfect image, and well, this is, sorry, a perfect image, and this one has sharp, or the edges have like 1 value, 40 value, 82 value, and etc. We could do this by hand, but there's a lot of work. And with that, I just want to see if, well, the problem was that we classified this before with the one, so it was very, very hard for the for the net. Uh, let's see if a number one can make it better. In this case, this is a one, and the categorical says here it's a zero. Oh, that the problem. It's classifying well. Remember the thing I mentioned about the no, the categorical. It's zero. So yeah, this is a one. That's the problem. Net. So let's check the net one. A seven. Hmm. No, I was thinking wrong. But the thing is, here we check this correctly. We create our own images. Like, I mean, I can delete this now. We create on our images by hand, not handwriting, but coding this image. So this is a perfect one. Maybe if we move this a little and make it wider, like from 14 to 16, still being classified as a 7. Mm, and what about if I put this to 26, no, 21, and this from 7? I mean, it's the middle. Now it's classified as a 1. Okay, better. What about the net 0? No, sorry, net 1. This says it's a 6. Okay, but you get it, right? You totally get it. And to finish this session, I want to make a wrap up of the whole idea here. Remember, the first part comes having a good data set. In this case, MATLAB provided to us the very, very good data set with the these data folder that contains subfolders with the label of 0 to 9 digit numbers, and inside containing the 1,000 images for this analysis. These 1,000 images were already prepared, giving the information of the black and white tone from 0 to 255, the 0 values for the black background, and the 255 value for white. In this case, remember, we draw a perfect line. This should be a 1. But our training data was composed of not perfect lines, was composed of handwriting. And so that's good because it's supposed to have mm, errors, to have less. If you push harder, for example, the pen or even the e-drawing pen, the value should be much bigger because the edges has less contrast and etc. And that's what we appreciate here. For example, the blurry here on the number edges. So the model learns to identify that, and it helps the model. Maybe not us, maybe for us it's simpler to see this type of images, but that's how we learn as humans. The model learns for the data we give it. So if we create 1,000 of these kind of lines and we pass it to the model, maybe the model can start understanding what this line is not a 6. This line, this perfect straight line, it's a 1. And a perfect square like the previous one we created, it's not a 9, it's a 0. So that's why our model start to create wrong classifications. At some point, it created good classifications, remember, but not always. What else? Well, returning to the data, this data was already prepared for that. Then we used the network designer to create an image input layer based on the input size, the combinational layers in the middle here, connect to a batch normalizer. These batch normalizers helps the accumulation of layers related to an activation function, in this case a ReLU. And for this net one, we just made that. So this is a six layer network, but you can not count the softmax, the fully connect, and the image input. So this actually it's a three-layer network compared to the previous one we created on code. Uh, let's see if this one to open, which was the same, but a three block of this combination to the layer connected with a max pooling, which helps reducing the computational effort for this. But remember, there are plenty architectures here. So we can check this about advanced things, and trying to code this could be complicated. So the let's this change. The deep network designer already comes with built-in of these architectures. So I found this amazing. And having the ability to connect them as blocks, not only in code and not only with classes, not only with arrays, but with this kind of code, block of codes, found it amazing. So the ability of creating now these more complex architectures, it's more of processing the data, of understanding that garbage in, it's garbage out, that it doesn't matter if we train our model correctly, if we test it with not the correct use cases. So if you're thinking of doing a classification for these type of images, maybe it's not worth it to have a handwriting dataset, because again, this is not handwriting, and it's very difficult that a person creates a one with a straight perfect line of 255 values every time, or a zero with a perfect square, right? Because zeros not are even squares. We needed to sharp the edges to see if maybe the zero classification will comes. But yeah, so that's the main idea here. So same as these deep learning toolbox that MATLAB has, there are other toolbox that are powerful for the artificial intelligence that we want to create. And remember, if we open the the deep network designer, we can't import architectures of neural networks that are on TensorFlow and PyTorch. So I think that's really, really cool. So you don't have to start from scratch. Um, I think that will be all for this session. I have a great time with you, and I don't know if you have any questions regarding these neural networks for artificial intelligence. We take a look to neural networks. I want to specify that in this case, we call them deep neural networks, not for the complexity, but because of the feature extraction. Remember, what makes a deep neural network, it's not the number of layers it has, it's the feature extraction. So In this case, we're not saying to the neural network, taking count the edges on, or taking count the patterns, if this is a stick or it has a round, or for example a round and a stick, it's a 9, or a pure stick is a 1, or two round circles are an 8, etc. We didn't say that. That is what makes this a deep neural network. We could make this with indicating the neural network, the features, and that will be just machine learning. Yes, neural network, but not deep neural network, or also known as DNN. And also, we make use of CNNs, which is convolutional neural networks, for the image extraction, because images are complicated. Again, they are very, very cool, but it requires a lot of processing, even though these ones were just one dimension, right? Because of the black and white. There are many topics about artificial intelligence, machine learning, and deep learning that you can take a look here on MATLAB. I mean, it's not the only tool, but it is a great tool. And that was one of the reasons for this session. Uh, I know it is not free to use, but if you have the license, go check this out. I still have three more sessions coming up. One, it's the at the end of this day, actually, 10 p.m. for me, or 12 a.m. for tomorrow, ET time. And we are going to explore quick implementations for machine learning, artificial intelligence in the web. In this case, we are going to use TensorFlow JS, and that will be a very, very practical session. And also, that will be just part one, and that's all. And also, I have another session for reinforcement learning, which is the other type of machine learning. In this case, we explore how to say this. In this case, we explore supervised learning, because we had the zero label images, the one labeled images, two labeled images. So we knew at what moment exactly we were passing one label to the network. What I cannot give a session about it's on supervised learning, because I haven't tried it. I know it's very, very interesting. But the other one I want to explore with you, it's reinforcement learning. MATLAB also has a reinforcement learning toolbox, which I encourage you to check. I haven't tried it, but I heard that it's really cool. And I saw a couple of videos, and it's like this, like super intuitive once you get the core concepts. They have a designer and everything. So MATLAB, it's great once you have the concepts understand, and it's great to help you understand those concepts because they have all well documented. But we are going to the other side of this, and we are going to do this reinforcement learning path with Python. So that will be the session of not tomorrow, but the other day after that. um, and well, that just to so join me for my next sessions on machine learning, artificial intelligence. Thank you a lot for joining me in this one. I hope you learned a lot, and I hope you liked what we built this session. um, Learned so much. Thank you, Alberto. Thank you so much, Alberto. By the way, the dishes are done. Amazing. I can put the paper plates away. Cool. Might be there. I will try to be there. Oh, midnight here. I'll try to be here there. Don't worry if you missed the live session. You can always watch the recording, because I know we need to sleep. So, thank you. So nice to see you again. Thank you too, Sky. So, thanks a lot for joining me, and well, spread the word. Happy hacking, and it's a pleasure again. Bye.